Let us now discuss the method of maximum likelihood estimation. Remember, we have an observed sample y1 to yn, and we had assumed a simple example. So these are n matches, and Sachin's scores in each of these n matches are given by y1, y2, and so on. So this is our observed sample. We can also denote it by a vector y. And what we are trying to do is estimate the parameter theta, which is the weight of Sachin's bat. And theta is the true parameter. We can never possibly know what we are trying to estimate is what can be inferred from the given observation. So we are interested in finding out the estimator theta hat, right? So this is the parameter estimation problem that is at hand. What does the MLE method fundamentally do? What the MLE method does is it assumes different values of theta hat, and that value of theta hat for which, observing this given sample, the joint probability of observing this given sample is the largest, that value of theta hat is the correct theta hat according to the method of maximum likelihood estimation. Let me repeat that again. In the method of maximum likelihood estimation, there are several possible theta hats. Out of all those theta hats, that value of theta hat for which the probability of observing this sample is maximum is the correct theta hat. So how we write it mathematically is we find out what is the joint probability of observing the sample as is observed in reality, and this function, we define a function L of theta. Why is it a function of theta? Because we keep on assuming different values of theta, and for each of them we will be able to calculate the joint probability f of y1, y2, and so on till yn, right? So this is given theta, and then we can assume different values of theta and find out for each theta what would be the value of this function, right? And this joint probability in vector notation, I can also write this is a function of the vector y given theta. This function has a name. This function is called the likelihood function. Likelihood function, right? And that value of theta which maximizes this likelihood function is the correct theta according to the method of maximum likelihood. So which value of theta maximizes L theta is the question that is to be answered here. So MLE states that that value of theta which maximizes the joint probability of Sachin scoring y1 in the first match, y2 in the second match, y3 in the third match, and so on till yn in the nth match is the correct estimator of theta. The way we write it mathematically is theta hat, my estimator, the MLE estimator. So let me write it down. Theta hat would be my MLE estimator. And theta hat would be given by argmax of L theta. That value of theta for which L theta is maximum will be the MLE estimator theta hat. Let us see if we can further simplify this problem. So we are trying to simplify the likelihood function, and if we assume that Sachin's performance in a match is independent of the other matches, then we can use some properties of independent events. So if you recall from your basic knowledge of probability and statistics, the conditional probability of A given B is given by the probability of their intersection divided by the probability of the event B. This conditional probability would be nothing but equal to the probability of A if these events are independent. If A and B are independent, then it doesn't matter whether you are conditioning A on B or you are taking just the probability of A. So therefore, probability of A given B is equal to probability of A. And using this part of this equation, one can write that the probability of A intersection B is nothing but probability of A times probability of B. So the joint probability becomes a product of individual probabilities, which are also called marginal probabilities. So the joint probability is equal to the product of the marginals. This property of independent events can be used if we assume that the sample that we have in each observation within that sample is independent of the other. So therefore, the joint probability can now be written as the product of f of y1, f of y2, and so on till f of yn. Right? So in terms of product, we can write it as pi of I equal to 1 to n f of yi given theta. Here this term pi represents the product. This is similar to the summation. So when we are taking summation, we write sigma I equal to 1 to n. When we take product, we write pi I equal to 1 to n. So this is product and this is summation. Right? So now we have used the independent assumption. Now remember, in all these discussions, it is important to note that the functional form of f has to be known from beforehand. Unless we assume certain functional form for f, we cannot be calculating these individual probabilities, right? So here functional form of f has to be known. If you recall, we had looked at a functional form in one of our previous examples where f of y was given by theta times exponential of minus y theta. So that was an example where there is one single parameter theta and the functional form is an exponential form. So similarly, the functional form of this function f always has to be known, otherwise it is not possible to calculate these individual probabilities. So now we have the likelihood function written in terms of the product of the marginals. What else can we do? It is often convenient to work with the logarithm of this function instead of using this function itself. The advantage of a logarithm is that logarithm is a monotonic function, which means that whatever theta maximizes L theta will also maximize log of L theta. So the next advantage that we are going to use is use the logarithm of this function. And what happens to the logarithm of the product? So log, I am going to write log or ln interchangeably unless I otherwise categorically mention. All the logarithms that we will be writing in this course would be logarithm to the natural base e. It is not the logarithm to base 10 or base 2, right? All the logarithms that we write are natural logarithms. So log of AB the product is nothing but log of A plus log of B. So the product now becomes summation. So when we use the log of the likelihood function, we have another term here which is capital L, and this is what is called the log likelihood function. And that is given by the log of this product, which essentially is the summation, right? So this is my log likelihood function. And what am I going to do to find out the maximum likelihood estimator theta hat? We need to maximize this L theta. So theta hat can now be written as argmax of capital L theta. So that value of theta that maximizes the log likelihood function is the MLE estimator theta hat. And what do we do for maximizing a function? We differentiate it and equate it to 0. And that's what we are going to do in the maximum likelihood estimation method.